Yeah, so good morning, everybody. I hope your Facebook assignments went well. A little bit topical with Facebook going out yesterday and a whistleblower for Facebook testifying before Congress today. So that was a bit amusing, I think. I had nothing to do with the Facebook outage. All I did was assign you guys the assignment to do a Facebook replacement. That's all. Okay. Okay, so let's look at let's look at my solution, I guess, for Facebook. Okay, so here we got a person, and I use the mutable trick that we talked about last time. I didn't see the link. Yeah. Okay. So the mutable trick is needed because if you have a key, the key can't change if you put it into a set, but the values can. And so what I did was I just made the connections mutable. And then that allowed me to modify it directly. A lot of people were copying a person out of the database of all people, and then modifying the copy, and then throwing the copy away. So that was not especially useful to do so. So what I did was I just would operate on the connections itself using a mutable member. Okay, no default constructor. That protects us. If you set a constructor equal to delete, then if you ever try like making just a person with no name, person P, it's going to throw an error, all right? Because there's no default constructor. And that's, again, why I require 41 for this class. I didn't used to, and it became really frustrating to a lot of students that hadn't had 41, because it's really nice knowing how to do classes and things like that. So anyhow, so this deletes the default constructor. There's a lot of probably new stuff. And that's one of the things that I really like about this class, is that not only is it math, but it also gives me an opportunity to keep pushing your C++ knowledge forward. Okay, so show of hands in chat if you've never seen a default constructor deleted before. Yeah, so you can do that. And if something should always be constructed with like a name or something, then this stops you from accidentally making people with no name. Right? If you make a vector of people and you give it a size, those will all be default constructed. So this will stop you from making a vector of people as well. You can make a vector of persons, it just can't have a size. That's fine. But, well, vector doesn't describe a type, but yeah. But if you give it like a size, then it would try making 10 default people, and the default constructor doesn't exist. Okay. Get username is a standard get function. It's marked as const. You should always mark things as const whenever you can. That's just good practice. And we're returning a string, so that's all it's doing is returning something, so this is a constant method. That's different from returning a const string, right? If you put a const here, this is a different meaning of const. This means the string is returned as a const, but it doesn't matter because it's a call by value return. Anyway, so yeah, the const in front of a function is different from the const after the function name. Okay. Set username, string new username. So it's a standard setter. Add connection, and here we have just another name. So we put another name into our set if it doesn't exist already. So we just call insert, onto the set. It's going to delete the duplicates, which is what we want. And connections.insert actually returns 2 values. And so this thing here is called a structured binding. It was added in C++ 17. And it basically creates 2 variables at once. And this insert function here returns a pair. A pair is a type that holds 2 values. Like that. Okay. And when you return a pair from a function, you can unpack them into their component parts. So the component parts are normally cout x.first and x.second. x.first would be 5, x.second would be 7. Okay? So normally it's going to return a pair. You take the pair and then you unpack the pair into, sounds like I'm talking about fruit now. You unpack the pair into the 2 variables, right? The structured binding here does it all automatically. So the first element of this is returned as the iterator. The second is returned as inserted. And since when does insert return values? Yeah, you want to know if it succeeded or not, right? So it returns a pointer, an iterator technically, to the element that was inserted, and it returns true or false. So, you know, did the insert succeed? Useful if you want to detect duplicates and things like that. Okay, get connections is returning a set, and this is a const. This here the const matters. Here the const doesn't matter because it's returning a copy anyway, so it doesn't matter. The thing here is returning a const, so that you can't modify connections by accident. So if you return it, then it's going to return a const set string. But here's the cool thing. You can modify it because it is marked as mutable. Okay. So even though everything's const, everything's marked as const, you're still able to mess with the BST because it is marked as mutable up here. Okay. So it's const, but not really. Well, yes, but actually no. Okay. True or false has some other person been added to us. So like if I'm Bill, and I don't know if Yoxthamer is my friend, you call is added Yoxthamer passed in here, and it will call the find function on the set, passing Yoxthamer. It returns an iterator, and again we use auto usually for iterators because iterator type names are really annoying to deal with, and they're just like this long, you know. And then if the person was not found, it returns a pointer to the end. The end is not an element in the binary search tree. It's a sentinel value or a dummy value that doesn't exist in the tree, but it exists sort of, and it returns a pointer to it to indicate not found. So if it was found, it points to something in the tree, and if it was not found, it returns a pointer to this dummy value. And so that's how you check to see if somebody's already in the tree or not. Okay. And you could probably use count as well. Rather than doing is added, you could probably just return count connections dot count like that. So that would be equivalent to that. It's a little bit less typing. I would probably do that, but I put this in here. I put this in here so you can see how find looks like. See what find looks like. Yep. So, yeah, count returns an int, but the int's always going to be either 0 or 1. So that's fine, returning that as a boolean. Works just fine. Any questions about that? How find works, insert. These are your basic data structure commands, right? Search, insert, delete are the three big ones, and then update. Okay, so because you notice I don't have an update in here, that's because the set itself is going to get messed with outside of the class, which is not great design. Nah, it's really not. Okay, so let's see here. Have a person, so we've got, so what I did was I made a all, and I think you guys had this too, right? This is in the starter code, right? An all, like it just holds all the people. Okay. And so if you're gonna add a person, first thing you do is you check to see if they already exist. So you find them. You can also use count as well. Again, I'm trying to teach you guys more computer science in addition to the math stuff. So we search for the person. If we get end, that means they're not in the network, which is good. Like if we're adding McCohen, if they're already in the network, then we're like, no, right? But if they're not in the network, that's good. So we add them to all using insert. You see how like small and compact this code is? Like, if you had to write the data structure yourself, prone to errors and bugs and crashes and all that stuff. If you use the standard library, all those pointer issues go away. The performance issues that you screw up on go away. The amount of code you have to write is like yay big, and it can be even smaller if we use count instead of find. Okay, in network already. Error. McCohen's already in the network. Okay. So here we go to add friend and follower. Okay. So you guys know about the ternary operator, right? So the ternary operator is like an if statement, but it's an expression instead of a statement. What's an expression? What's a statement? An expression is anything that can go into parentheses, like 5 plus 2, or the ternary operator, or CN technically, because it'll cast it to a Boolean. The ternary operator, whereas an if statement, statements require semicolons, right? So you can't put an if statement here. Like you can't write if. That doesn't work. It can't be embedded inside of something like that. So the ternary operator is a little bit of magic. It's saying, is Facebook true? Is Facebook true? And remember up here we chose whether or not we'd be in Facebook or Twitter mode. So is Facebook true? If it is, then enter the name of the person who will add a friend. And if Facebook's false, then add a follower. So Facebook has friends because it's bidirectional. And Twitter has followers because it's a one-way relationship. It's unidirectional. You can follow somebody without them following you back. They can follow you back, but they don't have to. Facebook, yeah. So if Facebook is true, this is what this is saying. If Facebook is true, then the expression evaluates to friend. If Facebook is false, then the expression evaluates to follower. Okay. And you can embed this right into a cout or whatever. So pretty cool. What if I got the const char star issue and did static cast to string instead? Would that be okay? Where? What issue? So we then read a name in from the keyboard, create a person out of the name, If we're using the read library, we could do that all in one step, but whatever. And then we find them to see if they're in the network. If they're not in the network, then we error out. Because for this one, if they're not on the network, it's good, right? Because we're adding somebody to the network. But for this one, if we're trying to make friends between two people that don't exist, or one of the persons doesn't exist, then that's an error. Like, the people have to exist by this point. Okay, so we search for person 1, person 2. Once we're sure that they're both in the all people's database, then these iterators here are going to be pointing at them. So this iterator here is pointing at Bill. This iterator down here is pointing at McCohen. We know both of them exist. These are pointers, essentially. They're iterators, but they're pointers to their location in the database of all people. And what we're going to do, if we're in Facebook mode, is we first check to see if Bill has added McCohen already. If they have, it's an error. If they've added me, it's an error. Technically, for Facebook, you shouldn't need to do both checks because they're bidirectional. So you technically only need one of them. But I don't see why we need both. But either, whatever. Add new Facebook friendship. So then Bill will add a connection to McCohen, and McCohen will add a connection to Bill. And this is working through the power of pointers, essentially, iterators. So we're pointing at Bill somewhere in the data structure of all people, pointing at McCohen somewhere in the data structure of all people, and then we're calling add connection on them. Now, add connection can only be called because it's a const method, which seems really weird, right? Because we're modifying this value. Adding a connection is going to call insert on us, but it's marked as a const method. And the reason for that is because elements in a BST, a set in the standard library, are all constant. They're all held as constants. And so the only thing you can call on a constant variable is a constant method. So everything here is marked as constant, even when it doesn't make sense. We are literally modifying the thing, but we're marking it as a const method. That's why I said this mutable thing comes off as like a kind of a giant hack, I guess. But, you know, as long as, you know, that it's kind of working around a limitation in the language / standard library, because you can't like half const a variable. You know what I mean? Like when you put something into a binary tree, that thing has to be a constant from then on. Because if you allow it to be modified, then it can break the tree. And so if you want to have a half constant, then you have to mark the things as mutable that you want to be able to change. And so this sort of, it's sort of a hack, and it's sort of like, it's just kind of a limitation in the language. You can't mark this as const. And even if you could, the BST wouldn't know that that's the key. Like it doesn't have any concept of like key and value in this sense. The key is the value for a set, actually. It doesn't know what's along for the right. Let's put it that way. Okay. So static cast. No, there's absolutely no reason to do that static cast. This works just fine. The reason why it probably worked for you was because you needed the parentheses there. Because there's an order of operations issue with double left arrow. Double left arrow actually has a much lower. The priority on it is from the bit shift world, and that's caused issues over the years. And so some of the times when you need to see out something, you just need to slap whatever is within here into parentheses, and then it'll work. Okay. So, yeah, this thing is kind of hackish, and it's kind of just an elegant solution to the fact that this C++ language can't have half const, right? So we are calling a constant method that modifies the thing. Okay. What languages do that better? Arguably Rust, and I don't know if it this particular problem. I don't know if this particular problem is solved in Rust. I've only had minimal exposure to it. But one of the things I do like about Rust is that all variables are constant by default, which is kind of good practice. You might want to get into the habit of marking every variable const if it doesn't not need to be. Right? In Rust, just every variable is const by default. If you want to mark it as mutable, you can. If you want to make a regular variable that can increment and stuff like that, you put a mut, M-U-T, in front of it. And then that variable is marked as not const. C++ is often described as a language that is beautiful, but all the defaults are wrong. For example, when you do inheritance between two classes, it defaults to private inheritance, which is the least useful way of doing inheritance. Variables, like, yeah, and there's other things you can add to a function, like no except, that notes that your thing doesn't throw an exception. There's a lot of things that probably should be standard, but can't be for historical reasons, right? It would break existing code. Okay, but yeah, I do like Rust. I've been kind of poking at it just a little bit, and it does a lot of things right. It solves a lot of problems in C++. But you know, I like C++ too. So. All right, so and then this code is going to be the same. So here's Facebook, here's Twitter. Twitter, you only have to check one relationship to see if person 1 is followed by person 2, or is it the other way around, or is following person 2. And then it's a one-way relationship. So right here is the difference between Twitter and Facebook, right? With Twitter, it's one directional, and Facebook, it's bidirectional, right? Person 1 adds person 2, person 2 adds person 1. Okay. All right, so print all of one person's followers, and the S suffix here, by the way, means make it a string class. This is no longer a const char star; it's a string. So, you can do that, Aaron, rather than, where was it? Right up here. So if you wanted to static cast that to a string, you could, or you can just add the S suffix there, and then it becomes a string. With Facebook, yeah, technically you only need to check one of them, because if person 1 has added person 2 as a friend, then person 2 would have added person 1 as a friend already. You don't need this check. Technically not needed. I put it in there because I didn't necessarily trust myself to not mess up. Yeah, so it could be deleted. Probably should be, arguably, but it's just an abundance of caution. If I had to do a refactoring pass over this, I might pull it out. Yeah. Okay. Depends how performance critical the thing is. Okay, so print everybody's followers of Bill. All right, so we're going to find Bill in the all persons database, and if they're not found, then can't print out their friends. We're done. Do something else. Okay, then we're gonna get the network. So all of Bill's network here, and then for every name in the network, we print it. Are you guys familiar with range-based for loops? How this works here? You might have used them a lot with vectors, but with sets, it works the same way. And it's in fact going to print them all out alphabetized, because it's a set. So I've gotten into the habit of using them more than regular for loops. Yeah, for something like this, where you just, if you're going to iterate over an entire container, it's just the natural loop to use. If you only need to do half the container or something, then I would probably use a regular for loop. Okay, print all the network of one person. So this is the learning point for today. So you guys ready for this? You guys fallen asleep yet? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 11 people online right now. Not yet. Okay, so see if there's anything else. Yeah, this is the topic for today, and it's going to be your this graph traversal algorithm that I had you guys implement is very common, and it's going to come up in a lot of graph theory programs. How to traverse a graph. Okay. It's your secret, Kearney. I'm always falling asleep. Yeah, that's why I drink so much coffee. Okay, so what you do when you're doing this style of graph traversal is you keep a list of all of the nodes in the graph you've processed already, and a list of all the ones you're going to process. And I'll draw it out on one node in a second, but I'll just go through the code real fast. So we start off by just adding Bill or whatever to the toProcess list. So we have one name to process. And if I don't have any followers or friends, it'll just print out Bill and be done. And that's a bug that a lot of you are getting, and you were getting it because when you were adding friends, you were adding it to probably a duplicate. You're copying it out, adding a friend to the copy, and then throwing the copy away. That was a very common mistake. Okay, so this is graph traversal. Not too big, and a lot of it's comments. But if you learn this pattern, it will serve you well, because we're going to be doing lots of graph theory in this class. So this is all the people we've processed so far. So it starts off empty. This is all the people we need to process. It's like a queue of names to process. And it starts off with just Bill in it. Okay? And then while there are people left to process, then we grab the first element out of the queue, essentially, which Bill will come off, or it actually doesn't come off yet. It just returns a pointer to Bill. And that's just a string, right? And then, so we get the string here, Bill Kearney, whatever. And then we find that person in the all network and get the connections. And so this is going to return a const set of strings. I think this might actually be no, it's a reference. It returns a reference. So it does not do a copy. Okay. And so this is going to return essentially a data structure holding all of Bill's friends, but it doesn't make a duplicate or anything. It just returns a reference, which is a pointer that doesn't look like a pointer. And then we say for every name in the network, if we have seen them already, if we've already processed that name, skip, right? Because, like, let's say I'm traversing the graph. I've been processed already. We get to Yoxtheimer. Yoxtheimer has me as a friend. It's like, oh, should we add Bill to the toProcess list? No, don't add it back into the list of things to do, because then you're going to get an infinite loop, right? If you process me, and then you go to Yoxtheimer, then you go back to me, and then you go back to Yoxtheimer, then you're going to just fall into an infinite loop. So it's important to make sure that you have not processed a name already. And technically, we could check to see if they're on the toProcess list as well. But it doesn't matter, because if we try inserting somebody that's already on there, it just ignores it. So I noticed a lot of you were checking to see if the person was already on the toProcess list, the list of people we still need to process, and you don't need to. If you do insert and they're already in there, good to go. Okay, so basically we're just gonna I'll do this visually in a second. Let's just go through the code. So after I've added all of my friends, then I am done. I come off the toProcess list. I no longer need to be processed because I've been processed, and I mark that I've been processed. And you do this until the entire graph has been traversed. After you're done, print everybody in the process list. That's it. Okay. So, and then option 5 just prints everybody in the network. So let me draw this visually, because your next homework assignment is going to involve traversing a graph as well, except make sure I didn't break anything. Good. We're going to be using bridges for it. Okay. All right, so let's draw out a graph here. Okay, so let's say we have a graph. So we have person A who's friends with person B and C are friends, person A and C are friends, A and D are friends, and C and E are friends. Okay, and maybe we've got some people over here that aren't connected to the other ones at all. So this is not a connected graph. This is a disconnected graph. Okay. Okay. So here's how we do graph traversal in this class. We have a list of processed, which is everybody we're done with, and then we have the to-do list, the toProcess list. And so we start off, if we want to print all of the social network of A, we start like this. The process list is empty. We haven't finished anybody yet, and we just start off with our start. Here's the start here. We just add them to the to-do list, the toProcess list. Okay, now here's the loop. Step one, pop off the to-do list and add to processed. They're missing an S in there. And then add all of A's, all of current's kids to do. Yep. Unless they are on the processed list. That's it. And you can see from the code, it's actually not too heinous an algorithm. Okay, so here we go. So we're going to start off with A on the toProcess list. So we start off by popping it off and adding it to the process list here. A is now on the process list, and then we add all of A's children to the to-do list. So we're going to add B, C, and D, and then we loop. We do this loop until empty. Okay, we do this loop until there is nothing left to do. Okay, so let's repeat. Pop off the front of the to-do list. So B is going to come off the front of the list, gets added to the process list, and then we add all of B's children that are not already on the process list. So we look at B's children. We've got A. Nope, A's already up here. Don't add it again. If you add it again, you're going to get an infinite loop. That's why we keep track of where we've been. You know, you essentially are marking these things off as you go along, and you don't add something that you've already visited. Okay. So when we go to add all of B's kids, A is already on the process list. So we skip that one. So we try adding C, but remember how insert ignores duplicates. We try adding C, it's already on there. It doesn't do anything. So when we process B, essentially nothing happens. All that happens is that B comes off the to-do list, gets marked as processed. Sort of metaphorically speaking, we can mark these as processed like that. And then we go to the next one. We go to C. So C comes off the to-do list, goes onto the process list, and then we add all of C's kits. So we try adding A. Nope, A's up here already. Try adding B. Nope, B's up here already. Try adding E. Yes. Let's add E. Okay. Then we take D off. Add all of D's kids. The only one here is A. A is already on the process list. We're done. And then E is the last one to be processed. And it's got no kids except C. C's already on the list. To-do list is now empty. We're done. And then the code just prints out the contents of the process list. It's going to print A, B, C, D, E. And you notice how F and G, which were not part of our social network at all, didn't appear anywhere up here. So this is a classic graph traversal algorithm. And it's a pattern you will follow over and over when doing graph theory problems. Okay, do you guys understand that? What I mean by processed and to do, or to process, I called it. All graph traversals are the same. No, not necessarily. What we're going to talk about today is Dijkstra's. Dijkstra sorts the to-process list by distance. But this general pattern of having a list of nodes you've already finished and a list of nodes that are upcoming to process, you'll see that pattern over and over again. Is this DFS or BFS? It's neither. It's technically doing the traversal in alphabetical order. So just whichever names happen to be alphabetically first are the ones that get processed first. Because it doesn't matter. At the end of the day, we're printing out all of the social network alphabetically. So the order that we do this doesn't actually matter. For Dijkstra's, the to-process list is going to be sorted using distance from start. It's used for shortest paths. And so Dijkstra's is constantly visiting the nearest city or whatever. But we'll do that after the break. So let's go ahead and come back at 11. And the Facebook assignment has been graded. Look at those punched into the... Interesting. It looks like everybody except a few people did... There's a lot of 6, 7s, and 8s and 9s, which is interesting. But yeah, it's because the graph traversal part is definitely the hardest, and that was only like one case, I think, right? So there's definitely sort of a challenge to doing this. Okay, so let's go ahead and take a break and come back at 11. Peace. Okay, so let's learn some Dijkstra. So Dijkstra is one of the most famous algorithms in computer science. You kind of gotta know it if you want to be conversant in computer science. So what is Dijkstra's algorithm? Dijkstra's algorithm is shortest paths. So anytime you use like Google Maps or something like that, there's going to be some sort of shortest path that runs. If you're going to navigate from Fresno to New York City, you want to take the shortest route, not the longest route. I don't know what the longest route would be, right? Go up to Alaska or something, and then back to Fresno and back an infinite number of times. So if you got Fresno over here, and you got some... you guys all back? Aaron's getting coffee. Okay. So if you're thinking about these in terms of like interstates or something like that, then Fresno connects to Sacktown, and it connects to Bakersfield. Excuse me. So Bakersfield here. And how many miles is Sacramento from us? I don't know. 177. All right. How many miles is Bakersfield? If somebody wants to pull up Google Maps, we can do this more quickly. So I kind of want to get some accurate numbers in here. Bakersfield to LA. Anyone? Put on some Inca music. 110 Fresno to Bakersfield. How far is Bakersfield to Vegas? How about that? And then Sacramento to Vegas. 112 Bakersfield to LA. Okay, so it's exactly halfway. Really. Okay. 285 Bakersfield to Vegas. And then LA to Vegas. Los Angeles, Vegas. Yeah. And then Sacramento to Vegas. $269 LA to Vegas. Okay. And then Sacktown to Vegas. $562. Okay. And then I don't know. We can keep doing this, but this seems reasonable. Okay. And then let's do LA to San Diego too. Why not? LA to San Diego. $120. Okay, that sounds about right. All right, so we can make this graph as big as America if we wanted to, but this will do. So let's say that Fresno is our starting location. I'm going to mark the starting location with a star, just so we know where our starting location is. When you do Dijkstra's, what you're going to do, Dijkstra's is very similar to breadth first search, except with breadth first search, every edge has a distance of 1. With Dijkstra's, every edge is weighted. A weighted graph. A weighted graph is one in which the edges have numbers. Okay, so every edge has a weight associated with it, which is a number. And this makes it a little different. With breadth first search, you just simply add everybody radius 1 away, everyone 2 away, everyone 3 away. Yeah, so this is the 2 process list, right? And so basically, if you're starting with A, then you add B and E and to the queue. The process B, there's nobody to process. So we process E, and then we add C and H. We then cross E off, process C, add D, G, and F. Then we process H, because that's in the queue first, right? And then we add G and I. G is already in there, so we don't do it. Add I. So the way BFS works is you start with distance 0, distance 1, distance 2, distance 3, distance 4, and all of them come out like increasing concentric circles. Dijkstra's is the same way, except instead of each edge having a weight of 1, they can have a weight corresponding to how many miles they are or how many minutes it is, which is oftentimes more useful than miles. Because it doesn't matter if something's a mile away if it takes you an hour to get there. Like there were towns in North Dakota which so I don't know if you guys have been like following the energy scene, but like there's oil sands in Alberta, which is the Canadian province east of British Columbia, and they've been trying to build a pipeline to carry the oil sands and stuff out of oil products out of there to America. And environmentalists kind of blocked that because they think that pipelines are dangerous. So what happens instead is that there's this army of trucks that carries them south instead, which is arguably more dangerous. And there were towns in Nebraska, in North Dakota, that they had a wall of trucks going down them 24/7. And so there would be people who were like trying to get out of their house, and they couldn't. It would take them like an hour to like make a left turn because there was literally not a single gap anywhere within the road. And so the point being is that 1 mile isn't necessarily 1 mile. It sometimes is an hour of your life. And if you've ever driven in LA, you know that to be true. LA traffic is miserably bad. The only city that I think is worse in America is San Francisco. Okay. State of the energy industry just pisses you off. Yeah. There's a lot that can be said about the energy industry. Okay, so how Dijkstra's works. You have a... well, actually, let's put it in the same order as before. We have a processed list. And then we have a to-do list. Yep. Or a to-process list, whatever. And so this will be sorted by total distance from Fresno. So that's what makes this a little bit different from what we just did for the Facebook one. Makes it a little different from BFS. It's more or less the same pattern. Like I said, that pattern of having a list of everybody that we've finished with. We need that so we don't get a loop, right? So we don't come back and loop forever. You have to have a list of people you've touched and finished and processed. That pattern, though, of like popping off the to-do list, adding all the children, putting it on the process list, that pattern you will do in a lot of different graph theory algorithms. The difference for Dijkstra's, at least, is that the to-do list, rather than being sorted alphabetically, which is what it was last time, is going to be sorted by their distance from Fresno. Okay? We're always going to be grabbing the closest city off the queue. That's it. Okay, so let's do this. So we're going to start with Fresno, and we're going to add Bakersfield and Sacramento. So I'm just going to write Bakersfield as a B, and I'm going to put a little note beneath it showing how far away Bakersfield is. Bakersfield is 110 miles away. Do you guys get this terminology that I'm using here? I'm going to write down the name of the city, and I'm going to write down its distance. In C++, what you do is have your less than operator compare based on total distance from Fresno. That's not, in this case, it's the same as the edge weight. But like for Vegas, your distance from Fresno is going to be like 395, right? It's not 285. It's 395 because it's the distance from Fresno, not the distance from Bakersfield. Yeah. Just drove through over the weekend, 1 hour to go, 30 miles. Oof. Where were you, Connor? LA? Yeah. Yeah. LA traffic is super annoying. One of the best things about the pandemic, if I'm allowed to say that, is that LA traffic got a lot better when people started working from home. Okay, so we're going to add our children to, so we start off with Fresno. Fresno gets added to the process list. And then we add our children, Bakersfield and Sacramento. Sacramento is 177 away, like this. And these things are sorted by the total distance. So, who gets popped off? Who gets processed next? It's doing the thing. You're doing the thing. You're doing the thing. Okay, whatever. We'll just cross it off like that. Who gets processed next? B. UCLA to UC Irvine took 2.5 hours. Yeah. Lord, I visited a friend of the family at USC once, and it was raining, and it was like a 5-hour drive to go from San Diego to USC. Oh my gosh, it's terrible. Okay, I'm gonna have to quit OneNote. Sorry, it's being stupid again. Yeah, see, it works now. Okay. So we are going to process Bakersfield. Easy. Move this up out of the way a little bit. Okay. And so Bakersfield is going to get processed, and then we're going to add all of Bakersfield's kids to the to-do list. Fresno has already been processed. Here's Fresno. We don't do that. So we're going to add Vegas, and Vegas is going to come in with what distance? San Diego Terminal Sign. I heard about that. Yeah, that was cool. Be cool if we got some of that up here. Maybe put out some of the forest fires. How far away is Vegas? We're going to add Vegas here. What distance do we add for Vegas? 395, right. Because it is 395 miles from Fresno via Bakersfield. Right, so Bakersfield's 110 away, and so we just take how far away we are and add 285 to it, and we write down 385 here, essentially. Okay. So Vegas is on, or 395, sorry. 395. And then we add LA. LA is going to be 222 away. And so this is going to have to sort. So I shouldn't have drawn them quite so close together, I'm afraid. Okay. And so LA is going to be put in here at 222. See how it's always sorted by distance. Okay. And then Bakersfield's done. Cross it off. Next up is Sacramento. Sacramento is going to pop off. So we're done with Sacramento. Sacramento is going to come up to the process queue. Now, here's the killer thing. We're visiting Vegas again. Vegas is not on the process list. It's on the to-do list. So there's a possibility we have found a faster route to Vegas. Right? So as it turns out, Vegas is only 10 miles from Sacramento. It's a lie, it's a lie, it's a lie, lie, lie. Well, let's say it's 10. Then we have found a faster route to Vegas than what we have in here. Do you guys see that? So what has to happen is the distance to Vegas is going to change from 395 to 180. It's 187. Okay. 187. And then this queue is going to have to move. You see that? So this is going to go from being last in line, like Dio, to first in line. Okay. You guys see that? So the data structure, what you do if you're using a set is you would check to see if Vegas is in there already, and you see if the new route is basically Fresno to Sacramento to Vegas. You check to see if that route is faster than this route. If it is, you delete the old route and you put the new route in. Because every time you find a new way of getting someplace, it's possible that that new way is faster than the old way. And so that's the crucial thing with Dijkstra's, is that you're going to replace the slower route with a faster route if you find one. welcome back, Aaron. Does that make sense to you? So you do a search to see if Vegas is in there already. If it is, you grab the distance. The distance is just a member variable distance. And you see if the new distance is lower than the old distance. If it is, you update the distance and you delete it out of the set and reinsert it back in. Because you can't change it, right? Because this is the key. Right. That's the key. So you can't modify it in a BSD. But you can delete it and then reinsert with a new value. Or you can use a different data structure, but I mean, we've been using sets, and sets work fine for this. Okay. So yeah, so Vegas is now 187 away, and now we have processed all of Sacramento's kids. So Fresno's done, Sacramento's done, Bakersfield's done. Vegas and LA are the only two people left in the queue. So you'll sometimes hear it as like a working set and a finished set. There's a lot of different terms for the same things. I just call it processed into process because it just makes sense to me. Like the nodes we still need to process and the ones we've already done. I don't know. This makes sense to me. So Vegas is now closer than LA, so we're going to process Vegas. And let's say that there's this high-speed rail from Vegas to LA, and it only takes 40 minutes. Maybe these are minutes instead of miles. It doesn't really matter. So it's 40 minutes from Vegas to LA. Now they got the Desert Express up or whatever. So what's going to happen is that when we process Vegas, currently we have 222 as the... Oh, no, that would be actually longer. That would be 227. Let's increase the speed of the high-speed rail. 10 minutes from Vegas to LA. So basically we move Vegas up to the process list over here, and we're going to update LA with a distance of 197. Okay, and then Vegas is done. We then process LA. LA gets moved from the to process list, the to-do list, up to the processed list. Fresno, we'll put a box around Fresno. Fresno has 0 distance, technically. Shouldn't LA have the total distance from Vegas to LA? It does, yeah. So that's the thing, right? Before, our distance to LA was 222, right? Because it was 110 to Bakersfield and 112 from Bakersfield to LA. So before, LA was 222 miles, but we just found a new route going from Fresno to Sacramento to Vegas to LA that was faster, because there's apparently super high-speed rail between these connections here, and so we have found a faster route. Once we have processed it, though, once we've processed the city, we cannot find a faster route, because at every point along the way in Dijkstra's, we're always adding the person that is closest in the network to anything else in the network. So only some of the passengers die from acceleration. Yeah, you have to enter one of those like in sci-fi movies where they flood the chamber, and yeah. We're gonna go on the float in the expanse. Shouldn't LA have the total from Fresno to Vegas to LA? Fresno to Vegas to LA, yeah. So Fresno to Vegas is 187 plus 10 is 197. Okay. And there's one other question we need to write down, which is, how the hell did we get here? And so whenever you write down your distance, you also write down the city that got you there. Okay? And we'll cover that in a second. I just want to finish this. So then we process LA. Oops, that was the eraser tool. We process LA, and LA is now done. We add SD into our to-do list. SD is going to be 200, 300, and 317 away. And then that's the last one in the queue, so San Diego comes off and joins the processed list. And then we're done. So when the to-do list is empty, you're done. So San Diego is crossed off, and we now have a list of distances for every city in America, essentially. If you had the graph encompass all of America, you would pre-compute the distance from Fresno to every city in America. And that's kind of useful. But what's even more useful is you can use this for routing. And so in order to do routing, you have to have write down where you came from. So Forever War, yeah. That's a depressing book, by the way. It's set on like Pluto or something like that. Yeah. I tried reading that. Okay. You read it while you were in Afghanistan, yeah. Yeah, it's a pretty brutal book. Okay, so what city did we take to get to SD? Should be an easy question. What city was the one that we had to take to get to SD on our fastest route? LA. Okay. So there's one other thing we need to write down, and the thing that we need to write down is the city that took us here. Okay. So you don't do this after the fact. You do this while you're doing the processing, right? So like when we found a new route to Vegas, originally this had like a Bakersfield written down here, but we found a new route that was faster coming out of Sacktown, so we would erase the B and write down an SAC for Sacramento. And so there's two things you have to write down for every edge, or for every vertex, which is the total distance it is away from Fresno and the town that you took to get there. And so if you want to know how to get to San Diego by the fastest routes, which city was the fastest way of getting to LA? You guys remember? Too much. Okay. What was the town that we took to get to LA? Yeah, we got there from Vegas on the bullet train, the Desert Express. And then Vegas got here via Sacramento, and Sacramento got here via Fresno. So if you want to route, if you go into Google Maps, you type in, all right, take me from Fresno to San Diego, it's going to spit out directions. And the directions it's going to spit out are drive north to Sacramento for 3 hours, get on a bullet train to Vegas, get on a bullet train from Vegas to LA. It's literally a bullet. I mean, it's doing 500 miles in 10 minutes, so it's really fast. It's a hyperloop or something. But here's the thing, like, how do you look that up? You can't. You actually do it backwards. So when you want to find your route to San Diego, what you do is you start in San Diego and you see, how did I get here? Well, I got here from LA. Okay, go to LA. How did I get here? I got here from Vegas. Okay, go to Vegas. How did I get here? Well, I got here from Sacramento. And you go to Sacramento. How did I get here? I got here from Fresno. Okay, that's our starting node. So we're done. Now, when you print this out, you don't print out the directions backwards. So what you do is what? The route that you got was San Diego to LA to Vegas to Sacramento to Fresno. How do you turn that around and print it out in the other order? Anyone know the standard library function to reverse a vector or something? Very good, Sarah. It is in fact reverse. So you call, you'd be putting these strings into, or cities or whatever, into a vector. You just call reverse on the vector, and then you get, which would look like this, reverse vector dot begin, vector.end. And then it will print out Fresno, Sacramento, Vegas, LA, San Diego. And you can format this however you want it. Google Maps usually has like road, intersection, distance, you know. Right? So that's Dijkstra's. Very famous. Dijkstra's is spelled D-I-J-K-S-T-R-A. Okay. Very famous algorithm. And there are a lot of problems that are solvable with Dijkstra's. It's provably optimal. You cannot find a faster route because it's always it's always adding to the network the person that is the minimal total distance from Fresno. So if it wasn't accurate, if it didn't work, then there would be another city that would be closer to the starting city than this one, but that's impossible because we're always adding the one that's the closest city to Fresno in the to-do list. Okay. There can't be another one out here as long as all weights are positive. If you allowed for a negative weight, like negative 1,000, Dijkstra's does not work. So Dijkstra's only works if the weights are all positive. Okay. So if our trip from Vegas to New York takes us negative 1,000 minutes, then the shortest route from Fresno to Sacramento would be to come over this way and ride the bullet train between Vegas and New York an infinite number of times, and then at some point go to Sacramento 1 million years in the past or something. So Dijkstra's is dependent on the fact that the edges have to be positive. Are you going to code it? Yes. That's your next assignment. Okay. So it's basically the same code as the graph traversal for Facebook, except instead of sorting just based on name, it sorts based on the distance the city is from Fresno. The biggest mistake people make is that they'll write down the edge that takes them there, like the distance to Vegas is 285. No, the distance to Vegas via Bakersfield is 385, right? It's the distance to Bakersfield plus the distance of the edge. Did you guys hear that? The distance to Vegas is the distance from the previous node plus the edge, not just the edge. Right? The distance to Vegas is not 10 from Fresno. It's the distance from Sacramento plus 10. Okay. That's the biggest mistake people make, is that they'll like if it's 7 minutes from Vegas to New York, they'll write down, okay, well the distance to New York is 7. No. It's 187 plus 7. Right? That's the most common mistake students make. The previous distance plus however far you go along the road to get to the new place. Yeah. Used your sample graph heavy in the assignment. Yeah, it's fine. There's just a toolbox of like graph theory algorithms that we just use over and over again, and we're gonna get experience doing them. Okay, so let's talk about it on the server. And how many people here have not used bridges before? That's a question also. Okay, so let's talk a little bit about bridges first. In that case, yeah, you're going to visualize it. So you're actually going to visualize your routing, which is pretty cool. Here we go again. All right, so for those of you that have not used bridges before, it's a group based out of the University of North Carolina, UNCC, not Chapel Hill. Okay, North Carolina at Charlotte. Okay, and Bruges. Isn't that a city in Belgium or something? Bruges. capital and largest city of the province of West Flanders in the Flemish region of Belgium. Totally different. Bruges, bridges. And the really unfortunate thing is that there's multiple programs called Bridges at UNCC, of all things. So, what you're going to be looking for is really, none of those are the right ones. Okay. See. Bridges API, Bridges UNCC, GitHub.io. There we go. There's the right webpage. It's ridiculous, like how some acronyms just end up getting used over and over again. Like I once wrote a grant, and I'm like, we could call it STAR, STAR, and everyone's just like shaking their heads. They're like, no, man. There's already like 7 projects we're on that are called STAR. State Teacher, Accelerated Retirement, Survey of Technical Aptitude Requirements. Like, they just started rattling off all the... I'm like, all right, fine. Yeah, they've been working on documentation a lot. They actually made documentation their priority for their latest round of updates. So, it should be better now. This is Bridges. I've been working with the people who do it for a couple of years now. And you can see it's an NSF.
Bridges is an API that allows early computer science students to create interactive visualizations.
Here, let me I shouldn't get copyright strike for this, I don't think. It's part of a NSF grant. Let me stream this screen for you. Change your windows. Bridges main page. Okay. So what Bridges is, it's a way of visualizing data structures. And that's oftentimes the hardest thing for computer science students to do. Like you're making a binary tree, but you have a hard time like visualizing it in your head. So what Bridges allows you to do is it allows you to visualize your vectors, your arrays, your linked lists, your binary trees, things like that. Okay.
Bridges is an API that allows early computer science students to create interactive visualizations as early as their first programming course.
The primary motivation was to improve the retention
That's KR.
of computer science. We lose about 40%. So the idea was that we want to do something that would improve the retention in computer science majors. We want to do something.
So the one of the big problems in computer science is retention, which means keeping people from dropping out, because people start into computer science because they're like, I want to write programs and create the matrix and like hack, people and stuff like that and make video games. And then they get into discrete math and it's like, welcome to modular division. And people are like, I didn't sign up for this. This is not what I signed up for. And they drop out. So, so one of the things that KR here, he's a really cool dude. I like him a lot. One of the things that he cares about is increasing retention. So like especially in college first years that have never programmed before, a lot of times they have a really hard time in computer science. And maybe a lot of that has to do with like them lacking the intuition as to like what these things kind of look like in their mental models and things like that. And you're going to see Eric Saleh in the next one. I like him a lot too. He's got some really good ideas.
That would improve the retention in computer science majors.
It enabled students to actually have access to real-world data inside of the classroom. So that whenever they do assignments, they can do assignments on data that they care about.
We abstract a lot of the heavy lifting.
You see it's a binary tree.
It allows for the viewing of these abstract data structures within your web browser. It's easy to access and to see what you've created rather than just looking at text and letters.
It's not just, hey, I painted a pretty picture of my data structure, they're actually interactive. You can kind of reshape the graph using
Minimize my face.
touch interactions and highlight different things that are interesting rather than just having one picture generated.
The newest feature in Bridges is Bridges Games. It allows students to learn basic programming concepts while creating games that work not only on the web-based system but on their phones as well.
Bridges Games is going to be a breakthrough for Bridges. It's going to allow us to reach lower level students below CS1, but also reach students above CS2, which could be AI.
It's actually easy for instructors in Bridges to develop their own learning material. In my parallel computing course, I have written a library that students can use in order to learn more about functional dependencies inside of algorithm. By using it, they can understand how the dependency structure of algorithm look like, so that they can figure out how to make them parallel.
So over a period of 3 semesters, we actually followed computer science students and measured their learning gains, knowledge gains from semester to semester. Secondly, we also measured how well are they doing in computer science after they've taken this course in data structure. And so one thing we have found is when you did control studies, that the students who
Success.
Anyone know whose college that is? Yeah, it's a fair mistake. I honestly don't think that our college should have been named Clovis College, because one already existed. You know, like, I don't know. It seems like the kind of thing that you would Google first, you know, before making a second Clovis Community College. So I don't know. The old name of our institution was Willow International, which sounds pretty cool. It sounds like it's an international school, and people wouldn't know that we were just named after the street International. Remember when you got contacted by a high school from across the state of Texas? Yeah. They're like, hey, are any of your students willing to work with us? We're a high school right across the border from you in Texas. And I'm like, sure, you know, but, you know, just so you know, we're in California. And they're like, oh, never mind then. I'm like, okay, you know, I'm sure my students would have loved to have worked with you. Okay. But 2 years ago, we got contacted by the Department of Energy, based out of Los Alamos, you know, where they do the nuclear experimentation and stuff like that. And they invited us to participate in a hacking competition. And they're like, are you Clovis Community College? I'm like, yes, I am. And they're like, would you like to engage in a anything goes hacking competition? I'm like, I'd love to. And they didn't realize that I was not the Clovis College in Clovis. I never lied to them. I'm just like, yes, I am Clovis Community College. And so we were invited into this hacking competition. It wasn't really hacking. It was like a lot of, I mean, kind of a little bit like there would be like an HTML page that had like secrets, like you'd have to go to view source and view the, you know, it was like a puzzle solving almost. There'd be numbers, and the numbers would correspond to musical notes, and you'd have to recognize the musical notes were Frere Jacques, and then the answer to the puzzle would be the next note in the sequence or something like that. So it was a really cool competition, and we ended up doing pretty well. I think I can't remember the exact scores we got, but I think we came in second. That's what I seem to recall. It wasn't a competitive programming competition. Like, it wasn't programming per se, although you could write programs to like help you solve some of the things. Yeah, we did it at the Fresno State Library. I think there's a picture. It was called the Cyberfire competition or something like that. And we came in like second place, third place, fourth place, and fifth place, I think, in the nation or something like that. Let's see if I can find the picture of it. But yeah, after the competition was over, the local reporter from Clovis contacted me. I gave an interview. Again, them not realizing that we're in California. I don't know. I have the photograph of it somewhere. But yeah, it was kind of amusing. So yeah, frankly, it's not really their fault. We Probably should have called it something different, but whatever. California. Did they ever realize? No, they wrote an article in the local newspaper, in Clovis, New Mexico, and talked about how their computer science department had come in second place in this big competition and stuff like that. Yeah. No, I never lied to any of them. Never lied to any of them. I don't know. It's just confusing. I don't want to tell you. Okay, let's go on.
So far, it has been successfully deployed in many classes.
All right, so what we're going to do is get you guys signed up on the website. Let's see, switch is streaming here. So on the Bridges website, oops, this is too far. There is a place where you can go log in. And you can see some of my old stuff on there. So this is like linked lists here. And one of the neat things about it is that you can mouse over them and it shows you the information on what is in the linked list. And you can drag them around and it'll animate and stuff like that, so you can visualize the stuff. For this assignment, what you're going to be doing is doing Dijkstra's. And so here we've got the Korean Peninsula. This is actual elevation data taken from a GIS source. And the elevation data is at a certain resolution, like I think it's 5 kilometer resolution, something like that. I don't remember off the top of my head. Basically, every point you see on there, every pixel, is a 5x5 grid. And the coloring that I did here, I added a false coloring to it, is based on the elevation of the points. And so what you're going to be doing is, given a map, you're going to be given a row and a column, like in this case here. And then you're going to be ordered to navigate via the shortest path to some other place. And this one is a little bit different from your what you might think, because it's actually going to be using elevation to compute the distance between two squares on the map. So you can think of every pixel on the map as being a point on a node, a point on a graph. So this is a really, really, really large graph. Okay, and the connectivity is real simple. You can travel north, south, east, or west. That's it. So every point on this map is a vertex and a graph, and there's edges going north, south, east, and west out of each one, and the distance is based on a formula that's in your homework assignment. But basically, if it's like, let's say you're on a 1 kilometer grid, to travel from 1 kilometer east to west is 1 kilometer. But if there's an elevation gain, then there's a penalty to the distance based on the difference in elevation. And so what this algorithm is doing is actually, dang, I keep getting things in my eyes. I don't know what's going on. Maybe the ash falling outside or something. I don't know. And so the goal of the algorithm is actually to find the flattest route, so to speak, right? Like if you've got a mountain, as the crow flies, the fastest route is just to go over the mountain, right? Drive your Skyrim horse up the side of High Hrothgar and then down the other side, you know what I mean? But in real life, if you're driving a car, you don't want to drive up the side of a steep mountain and then down the other side, even though looking at it from above, it's a short distance. What you want to do is have as little up and down as possible, so it's actually faster usually to drive around a mountain if it's flat than it is to go up and down the mountain on the other side. So this is going to be your assignment. You're going to have a week to do it, and I recommend you start on it now so that when you get stuck, there is a crashing bug in the starter code I give you. I left that in there deliberately so that you can learn to fix bugs. Okay, here's the San Joaquin Valley. This is where we live. And you can see that there's a bunch of these valleys that kind of head up into the Sierra Nevadas. This is This is actual topo data. Like, I pulled it from the government's website before they took the tool down. The tool actually doesn't work anymore. When I first started doing this assignment, students would have to go and grab a chunk of land, whatever interests them, and do Dijkstras on it. And they actually disabled that tool. They broke it. It's not disabled. It's still there. It just doesn't export the data anymore in the format that we need. And so you could probably, like if you have Arcus or something like that, you could probably get this data via some other process. But it's before it would just give you an ASCII file, and the ASCII files were just like for San Joaquin, the ASCII files are just like how many rows, how many columns. Here's row number 1. Here's row number 2, and these are just elevations at each point along the way. Okay. So it's a giant 2D grid. That's it. Okay. So the first thing you need to do to use Dijkstras is to do the assignment, I should say, is to go to Bridges, and you're going to need to create an account. Okay. So let me back up a little bit here. So Bridges has a login button, and you can click on sign up here. Now when you do that, it's going to give you an API key, and this is something that a lot of places do. So like if you want to, and I'm not going to show it on here. Maybe I'll screenshot it for you, and then I can erase it. Let's see here. Oh, damn it. All right, might as well just show my API key. Thanks, Windows screenshot. Okay, so anyhow, this is what it's going to look like. All right, so there's my username. There's my email address. Don't spam me, please. There is my API key. Okay. And so what happens is whenever you use and you can always make a new one. That's why I don't care that much. So as soon as I hide this, I'm going to click on generate a new API key. But this is cool because I can actually show you how this works. So the API key is just a big number. And what you do is when you go up to cd up, cd bridges, let me deploy the assignment to you to actually sudo deploy homework, bridges, mountains, to seaside 26, bridges, mountains. People are entering and leaving the chat. Okay, so you have a copy of it now. So you can follow along if you want to. Bridges, mountains, .reference, then .cc. So what's going to happen is when you make your assignment, the first thing you're going to do is you're going to type in your username and your API key. Now you can see that API key is out of date anyway. Okay. So if I want to make this code work, I paste. Was it? No. Copy. One more time. Let's do this. There we go. So you have your username and you have your API key. Your API key is kind of like a password, except not as secure, right? Or it's not as important, I should say. So what happens is that if you accidentally reveal your API key, like I just did, because the Windows screenshot tool, even though I screenshotted monitor 1, it popped up on monitor 2. Thank you, Windows screenshot. Very cool. I can now generate a new API key, and no harm, no foul. All my old code will break until I copy and paste the new API key in. So what happens is you have to give it a project ID. The project ID is assignments. There we go. So where was my thing? My projects. There we go. So my projects, each one of these has a different number on it, right? So this one is project number 1005. Colorado.dat is 1004. Okay. So every time you run it, if there's a project 1004 already up there, it'll replace the old one. And so what you want to do is, if you want to save your stuff on the Bridges website like I did, then you change the project number. Like I was like, oh, that's a cool visualization. I like that. And so that one used to be called 1002. So I just changed the project number to 1003 so that it wouldn't erase the old one. Do you guys understand? So like when you're working on something, here's part of Australia, I think. When you're working on something, it'll keep overwriting the whatever the project number is. But if you want to save it, then you change the project number to something else. You guys understand that? Does that make sense? So, it's a long line of parameters in those functions. Yeah, probably. So, oh shoot, I shouldn't close that. So anyway, so you give it a project ID, you give it your username, and you give it your API key, and then that is what authenticates you on the Bridges website. So step one, get yourself set up on the Bridges website, get a username, get an API key, and then you're going to punch them in right here. Okay. So type in whichever project ID you want. The project ID doesn't matter. It's just used to determine what's going to overwrite what. You know what I mean? You're going to type in your username. You're going to type in your API key here, and that's what authenticates you on the website. Now, once you've done that, delete this line. Just like that. Okay? Or you can delete the comment too. D2D. And so by default, your code will not compile. And the reason for that is because the autograder basically will give you a 0 if your code doesn't compile. So if you didn't even do the 30 seconds of coding to get a username and an API key and delete these lines, you get a 0 on the assignment. Okay? So I put that in there so you don't try like coding it up first or whatever, because it won't work until you've got your username and API key in. Technically, I could probably make the static assert a little bit more intelligent, like it makes sure that your username is not username and your API key is on API key, but whatever. It's just easy for you to just delete that real fast. Okay, so this is a Bridges object. This is what is going to bridge the connection between your code and that website that does the visualization. So you just basically punch in project ID, username, API key. And you don't even technically need these 3 variables. You can actually just put those 3 variables into here directly and call it a day. Who keeps leaving and coming back in? Middle of class. Is that Mason? Okay. Alright, I'm turning on streamer mode. There we go. I don't know why that got turned off. That was probably when I screenshotted. I hit it by accident. Okay. So, this is the file that we're going to open up. We're going to open up Colorado1.dat by default. That's elevation, height elevation from Colorado. And if you run the program with a command line parameter, then it will open up that file instead. It calls the read data function, which is going to open up this file and basically put all of the data into this array. Wait, you said, this doesn't look like an array. That's just a pointer. Yeah, it's a pointer. And it's a pointer to nothing. It's not even initialized. It gets initialized here. Okay. So read data returns a pointer to the start of a big 2D array. If you want to refactor this and have read data, for example, return a 2D vector, you're more than welcome to. Did you guys hear that? You are free to not use a pointer. You can. It might be good practice for you to work with pointers, but you don't have to. You're free to convert that into a vector of vectors of integers. It's fine. If you want the practice, it's fine too. So a pointer in C++ and C is, for all intents and purposes, an array. I don't like working with pointers necessarily that much. Well, I mean, okay, I don't mind, I should say, but this doesn't tell me what is it pointing at. You know, is this pointing at 1 int or 1 million ints? You know what I'm saying? It doesn't carry enough type information for me to be happy with it. That's one of the reasons why. I mean, in high performance computing, we do this all the time. By the way, a vector of vectors is not performant for a variety of reasons, and has issues. So in high performance computing, we do this, but this doesn't contain type information for me. It doesn't tell me am I pointing at a single integer or an array of integers, and that's a problem. And if it's an array of integers, how many? How many? I don't know. So you have to have that held separately, which I don't really like. That's what classes are for, right? Classes are there to have variables that should be together, put together in the same type, right? So rather than having a name and an address and a social security, just as 3 different variables, when we make a class, we'll put them together into a class that has the name, social, and address in one variable, and then you can make a vector of that variable type, and the 3 things will go together hand and foot. Here we've got 3 different variables, width, height, and elevation data, and so these things are kind of tracked separately, and hopefully they don't get screwed up and out of sync. And in this code, it's fine. Like, the code's fine. So the read data function is going to return the width read into this variable here called width. It's going to return the height read into this variable here called height. It's going to return the maximum height into this variable called maxval, and you're passing in the file name, so colorado1.dat by default. And then it returns a pointer to a width times height. Elf data is a pointer to a chunk of memory of size width times height. Okay. So if it's 100 by 100, then it is a pointer to 10,000 integers. Yep. And how are they laid out? They're laid out in row major ordering. So the first row are all together, then the second row is all together, then the third row is all together, so on and so forth. So this looks like a 1D array, right? It's a pointer to a single address in memory. And so how do you know the memory layout? You don't. At least you don't know it from the type information, right? And that's, again, you know, one of those things. Like, are you interleaving, like, especially when you're doing image data, are you interleaving the RGBs? Are the RGBs separate planes? There's information about the data that a raw pointer like this doesn't have. So, is it standard? Yeah, this is actually, and the reason why we do this is because it's very performant, right? This is a contiguous block of memory, and if you know the memory layout is row major, which it should be, unless, I mean, I haven't checked in a while, but I'm 95% certain it is. Row major ordering is very performant. Your CPU is optimized for row major data. You get better cache performance and thus better runtime performance when you do this. And that's why I said in HPC, high performance computing, we do this all the time. This was my master's degree, right? It was in high performance computing. We don't use 2D vectors. I mean, you could, I guess, but like when you're trying to squeeze every ounce of performance out of a thing, you use a pointer to a chunk of memory, and you work with it. It's like I said, this is, you know, I'm not being critical here. I'm just saying that for those of you that have been used to using like vectors of vectors and things like that, you can refactor it if you want, or you can get practice with it. Either way. And if you're going to get practice with it, you're going to need to turn on address sanitizer. So if you go out of bounds, it'll tell you. Okay. All right. So we changed the title. So bridges is this variable here of type bridges, capital B bridges. And there's various things you can set. And one of the things you can set is the title. So it's going to be like Mountain Paths, Colorado, Greedy Algorithms. And that was the title appears right here and right here. So this is the title. And that's the title. Okay. And that's set here. You need to change the name of the title to be Mountain Paths Dijkstra's, because the code you're starting with is actually the finishing product of your CSI 40 version of this assignment. So some of you probably had me for CSI 40 where we did this assignment, and we did an easier version of it because CSI 40 people don't know Dijkstra's. So they get a very easy version. It's taken from a nifty assignment. This one here. So Stanford maintains a website of good computer science assignments, and you can see I go through it. It's Falling Sand I kind of want to do with you guys too. That's kind of fun. Paths, yeah. So Baker Frankie at Gmail came up with this one, and so the greedy algorithm, basically you go left to right, and there's only 3 choices you make. Do I go northeast, east, or southeast? And you just pick the one that's closest in elevation to your current elevation. And so it does kind of a rough approximation of Dijkstra's, but it only goes from like the leftmost column to the rightmost column. And you can see it kind of follows the contours of the ground a little bit. But you can't go from like here to here or something like that. But like if you started here, it would probably go through the canyons as much as it could, because at every point there's only 3 spots, and you just always pick the one that's closest. So that's called a greedy algorithm. A greedy algorithm makes locally optimal decisions that are not necessarily globally optimal. Okay, so we are, however, going to be doing Dijkstra's, and so we're going to have a starting row, starting column, an ending row, and an ending column. That's going to be entered by the user. So the user is going to be like, navigate from 1010 to 100 100, and then it's your job to Dijkstra's the fastest route to there. Okay. And right now the code in here is a greedy algorithm, and it is in a function called find path. This is the heart of the assignment here. You need to replace the greedy algorithm, which only goes left to right and goes across the entire map. You need to replace that with a Dijkstra's algorithm that navigates from start row, start call, to end row and end call. Then, after you've done the Dijkstring, you're going to mark the route. You're going to mark the route along the way with by setting the elevation to -1. So basically, you're carving a hole in the mountains as you travel along. You're gonna tear the mountains down and set the elevation to -1. Negative elevations aren't really supported by the algorithm. You could probably, like, if you get a negative elevation, you could probably set it to 0 or something like that, or set it to -2 and then colorize it separately or something. I don't know. Okay, so then finally you're going to make that color data, and so that's in a function called getImage. GetImage is going to take in the pointer to the chunk of elevation data, the width and the heights, because this is the C way of doing arrays, right? C arrays don't contain any type information as to their dimensionality. So you have a pointer. You need to know, is this pointing at 1 thing, 10 things, 100 things, 1,000 things, and you also need to know the size of a row and the size, the width and the height, right? How long a row is and how tall a column is, because otherwise your data gets screwed up. So we're passing in the pointer and the information we need to make the pointer work, and we're also passing the maximum value. The reason for that is because when you do the visualization, the default visualization here uses white for whatever the maximum value is. So if the maximum value is 3,000 meters, then white is 3,000 meters. If the max value is 1,000 meters, then white is 1,000 meters. And black is whatever the minimum value is. Okay? Or it could be sea level, one or the other. And so they do a little false coloring here. So this isn't actually snow here in Colorado. They actually just colored the tops of the mountains as white because that's the highest elevation. And then the low-lying levels are darker, as you see here. Okay. And what you'll want to do for your assignment is to do there's another Colorado map, is to do like some false colorization like this. So what I did was I colored the low-lying areas as green, and the green would kind of lerp up to a brown as they get up to higher elevation. Lerp is linear interpolation. Any negative elevation I color is this blue color to make it the ocean. I probably could have blended it a little better, but whatever. So any negative elevation I'm just coloring as blue, and then the highest elevations I'm making white, and then it lerps between white and brown, and then brown and green. And so it kind of makes the snow a little dirty looking, but overall the effect I think is kind of nice. It kind of is a nice false colorization. This is not a photograph of Korea from space. This is actually just elevation data that I applied a false coloring to. Okay, so took some experimentation, had some pretty gnarly, ugly results. Some bright orange Colorados and things like that. I don't know if I have any of these up here. I guess not. Okay, so that's your assignment. Oh, this is another one we're going to do. So this is actually routing. This is. Do you guys recognize the streets here? Anyone recognize the street map? Yeah. Yep. So this is Willow International, or Clovis Community College. And this is the 41 here. This is the 168. So what intersection is that, do you think? That's Friant. Anyone got Fresno geometry skills? Geography skills, rather. Herndon and Fresno? I think so, yeah. I think this is actually... yeah, I think the starting location is actually like... I think the Chili's on Herndon and Fresno, I think, was where I started routing from. It could have been the Kaiser. The Kaiser is like right up here. Or it could be Sweet Tomatoes or something like that before they went out of business. And so, yeah. And so Bridges has... This is really cool. It's got a OpenStreetMap plugin where you can query it and it will give you OpenStreetMap data. And all the vertices are locations in space, X and Y locations, essentially, latitude and longitude. And the edges are connections between them. And you can visualize the map. And in Bridges, when you visualize a graph, you can change the colors, you can change the thickness, you can change the shape of the vertices and things like that. So you can see this one here is purple, right? The starting location is purple. And then you can also make it a diamond or a star or something like that. And you can also make the lines thicker if you want. But basically, this is, I wrote a Dijkstra's algorithm that routed from Chili's to our college. And it colored the fastest route red. Okay, so Blackstone and Herndon. I think Blackstone's on this side over here. Yeah, that's Blackstone over here. So, yeah, you can see that's the Cloverleaf interchange there. Pretty cool stuff, you know. It's really amazing that that works. It's like we're connecting to the University of North Carolina, and they're connecting to OSM, and they're feeding us the data in such a way that it's very easy for us to get it, and then all we have to do is take their data and run Dijkstra's on it and get do Google Maps, essentially. So for your assignment, though, for Bridges Mountains, it's you don't even have to worry about the edges and things like that. It's a stripped down version of Dijkstra's, because it's a grid, right? And when you have a grid, every point on a grid is connected to all the points north, south, east, and west. Be careful on the edges. If you're on the top row, the left and right column, or the bottom row, then you can go out of bounds, right? So be careful of that. Always check your bounds. Always turn address sanitizer on. And so basically, you don't actually have any edge information. It's actually a simplified, stripped down version of Dijkstra's, because you don't actually have to grab edge data and things like that. It's a grid. And so the distance from one point to another on a grid is based on the grid size. I guess I'll minimize this. Plus, there is a penalty for. Okay, so each tile represents 1.8 square kilometers. So the costs are all in meters, and so to move horizontally has a cost of 1840, and a diagonal move has a cost of 2601, because it's Pythagorean distance, not Manhattan distance. But the key thing is there's a penalty for vertical, and so the penalty for vertical is 20 times the change in meters. So if there is a 100-meter rise, there is a 2,000-meter horizontal distance penalty. Okay. So what you're going to do when you're Dijkstring is you are going to go. You're going to add your starting location to the to-process list, and then you're going to add all of their kids, which is the 8 people: northwest, north, northeast, west, east, southwest, south, southeast. You're going to add all 8 kids to the to-do list, the to-process list. And the distance they are is going to be 1840 for the cardinal directions, north, south, east, west. 2601 for the diagonal directions, northwest, northeast, southeast, southwest. And then all of those will have a penalty added to their distance based on the difference in elevation change. So if they're the same elevation and you're traveling west, that's a cost of 1840. If you're traveling west and there's a 100-meter change, then it's a cost of 1840 plus 2,000, so 3840. So it's significantly more expensive to drive uphill and downhill. Okay, and then you just slap all of these things onto a to-do list. The to-do list should be sorted by total distance from start, and you process the grid nodes one after another. Always taking the one that's closest to start until you hit the end. Once you hit end, you're done. You don't have to do the rest. So this is a fairly substantial assignment. It's not long, like the actual amount of code for it is very similar to what we had with the Facebook. Like the code that I showed you for the Facebooks be very similar. There's just, you're going to be sorting not based on name, but you're going to be sorting on distance from start. And yeah. So once the end node pops off and you process it, you're done. Then you have to backtrack along the route. But just get that route, just get the Dijkstra's working first. Start with a test map. Okay? Don't try running this on Colorado or San Joaquin first. Run on a test map. Make a map of size like 5 by 5 or something, right? So so I made a little map. The file format is, like I said, it's just rows, columns, and then it's just a 2D array. So 0 elevation, 0 elevation, 0 elevation, 0 elevation, 0 elevation, 1,000 elevation, 1,000 elevation, 0 elevation, 1,000, 1,000. And so, do you guys see what I did here? I basically made like a maze, kind of. And so I'm going to navigate. I load the map, and then it's like, where do you want to navigate from and to? I say, give me from row 0, column 0 to row 4, column 4. And then I want to make sure that the route that it gives me is to go along this way, down to here, down left this way, down to here, and then this way. So one of the key things that I really try to emphasize in this class and all classes is start small, go slow, and learn to test your code yourself. What's wrong with my code? If you're doing it on San Joaquin, it's too big. Like you can't like there's too many possibilities. It's exponential, like the number of different routes you can take and stuff like that. So just make a little test map. Maybe 5x5 is too big. Make it, I don't know, 2x2, and just see if it, can pick the shortest path that way. I don't know, 3x3. Start with really, really tiny maps, and that will tell you if your bounds checking is working and stuff like that. So, do you guys understand what I'm getting at here? Like, you need to feed dummy data. Like, so many students, like, especially in CSI 40, like, their code doesn't work, and then they message me. They're like, why is my code not working? And, a lot of times my first question is, what have you done to test it yourself? Because that's a habit you need to get into. Like, where is it breaking? I don't know. And sometimes, like, I just help the CSI 40 student because it's like they got an error message they don't know. What does this mean? Like, you need to put an ampersand there or something, But if your algorithm's not working, you need to get into the habit of feeding some dummy data to your own algorithm and seeing how your algorithm behaves and seeing if it's behaving the way you expect. And if it's not behaving the way you expect, then looking at your code and trying to figure out why. See out all of the things, test all of the things, start small, go slow. Okay? You got a week to do it. It's not substantially different from what I just showed you for the Facebook. It's one minor change, where it's sorted by total distance from start rather than name. Okay. I gave you a tile class. The tile class looks like this. And the tile class, these are the vertices, okay, that you're going to be putting into the queue. To do process, it's going to be holding tiles. It's got an X and a Y location. That's the row and column. And this is remember how I said, like, when you get to Vegas, you have to write down how you got there? This is where you write down how you got there. So as you add a child to the to-do list, its from is you, right? So if I'm adding all of my kids from X and from Y is going to be my X and Y. And this allows you to backtrack along the route that you make and output a route at the end of the day. So every tile is going to have a row and a column. It's going to have the row and the column of its parent that it came from. It's going to have a distance, total distance from start here. No default constructor again, that's been deleted. And it's got a constructor that takes a row, a column, from row and column for the parent, and a distance. It's got a comparison operator, which is used for the data structures. And it's got a lesson operator, again, for data structures, and it is sorted using the less than operator, right? On distance. Okay. So it's the key here that it's going to be sorting on is distance. And so when we toss this into a set and pull out the first element we pull out is going to be the smallest, the one closest to home. Okay. And so I used a priority queue. A priority queue is a data structure that is optimized for finding the smallest value. That's what a priority queue is for. It sorts things based on distance, and the smallest distance is the one that comes off the top, and it's very, very good at that. So rather than using a set, I'm using a priority queue, and it looks like this. That's how you make one in main. So priority queue of tiles, the backing store of it is a vector of tiles, and then the sorting function is tile comparison, which is this. So that tells the min heap to be a min heap. So it tells us sort the tiles based on distance. And heaps are max heaps by default, so by flipping the thing around, we get a min heap. And then we're going to have a hash table. So the processed queue, this is our to-do list, right? Our to-do list is going to be made like this. There's the source code for it. That's the data structure you should use. Okay. our to-do list is going to be made like this, and our processed list of tiles that we've seen already, I'm going to use an unordered set because it's faster than a set. You could use a set if you're used to it. It's fine. No harm, no foul. But an unordered set is going to be a little bit faster. And so this is a list of everybody that we've processed. And I've created a hash function. I have a hash function. I'll answer in a second. I have a hash function because unordered sets are hash tables. And so if you're trying to put into a hash table something it doesn't know how to hash, you have to tell it. And this is the format that you use for that. So you actually have to add to the standard namespace a hash specialization for your class. And normally you're not really supposed to do this. Normally in the standard namespace you're supposed to leave it alone. Like you're not supposed to add things to the standard namespace ever, except when it comes to hash functions, because you have to add it to the thing. So what I'm creating here is I'm creating a specialization for the hash function. There is a hash function in stud. Stud has a hash function for all the stud types like ints and strings and stuff like that. I'm creating a specialization for tiles. And this hash function allows unordered set to work because it's a hash table. Right? Hash tables have to have a hash function. And so it knows how to hash an int, it knows how to hash a string, it doesn't know how to hash a tile. What the hell is that? I don't know. And so to hash a tile, we have to specialize the hash function. And so all this boilerplate stuff is just something you're going to copy and paste. Anytime you want your custom class to work with a hash table, you're gonna do this. Just copy and paste it. It's a little bit garbage. A lot garbage. Okay. So the namespace standard is because the hash function is in stud. And it is technically a class or a struct that has a operator open close parentheses on it, which makes it act like a function. So you'll be able to call hash looking like it's a function, but really it's actually a class with an overloaded parentheses operator on it. And it is hashing by just returning the combined x and y location. Essentially, it's the what it's returning is the index in the array. Sort of. Yeah. Sort of. It's sort of returning the index in the array the tile would be. And that guarantees a unique hash for every tile. So if your hash table is big enough, there will be no collisions in it. Okay, how do you guys feel about this? Then at the end of the day, you call on the bridges thing, set the data structure equal to the color grid. We just made the color grid is the visualization of the 2D array. And we call visualize. And then that connects to the bridges website. It updates your credentials on there and pushes all the data up. You get a hyperlink when you run it, and then you can open up the hyperlink and it'll visualize your thing for you. And I think read data is done. Yeah, I actually replaced the pointer with a vector of vectors. Added in min-val as well. Oh, is this my? Oh, this is my thing. Yeah, this is a solution. So this is the code they give you, and so you can see that I actually modified it. So I actually changed it from working with a int pointer to a vector of vectors, just so that I could do bounds checking inherently with it and not have the dimensions inherent in the thing. It's not as fast though. Okay. So yeah, if you scroll to this point in the video, you'll be able to see how I did the read data function. Be careful with water. Water is going to get you. Water is negative elevation, and be aware that if you have water, it's probably going to crash your code until you fix that. Yeah, I don't know. It's all pretty straightforward. Right now, the find path is the heart of the program, and the find path code right now is doing the greedy algorithm, and you can look at it to see how the how working with a 1D array that's a 2D array works. Basically, you're going to rip out the guts of find path, and you are going to replace it with Dijkstra's. Okay. So there's a lot to this. It's a pretty major assignment. So get cracking now. We've got one more class before it's due. So really, I'm dead serious about this. Try to get it done now, and you will get stuck, and things will crash and not work, and we can go over it on Thursday. I'm going to go to sleep early Monday night next week. I'm going to be tired. I'm going to be gone all weekend, by the way. I'm not going to be available to help you over the weekend. I'm going to be gone Friday through Sunday. Okay? And I'm going to be exhausted Monday. So, in 100% honesty, work on this now. I'm not doing one of those like professors like, don't wait till the last minute. I am 100% serious. Try getting it done now. And see how far you can get it until you get stuck. And then we can get you unstuck on Thursday, and you will succeed at the assignment. Okay? I'm serious. I'm going camping. I'm not going to have internet connection. So, if you're going to be like, I'm going to come back, and Discord's going to be like, all these messages, help, my code's crashing. Yeah. Do you remember how I said in class the water's going to crash your code? Oh, yeah, that's right. Yeah, because water is going to crash your code. This code does not handle water properly. It's going to segfault your code. Get water in your electronics. Okay? And all this 1D array stuff, you can work with it, or you can just tear it out entirely and do what I did, which was I just replaced with a 2D vector. A vector of vectors. So the algorithm itself is not hard, but this is a big, complicated assignment. This is a traditional junior level assignment that you guys are doing here. Okay, so it's a drought. Get rid of the water. Yeah, that's San Joaquin's approach, I think. Okay. Okay, so that's it for today, guys. Good luck. Gambate. Do your best. And in 100% seriousness, work on it now, work on it tomorrow, and then we'll come back on Thursday and I can answer your questions. Okay? Do not message me over the weekend and expect me to answer, because I will not have coverage. Okay? And if you're waiting till Monday night, it's going to be too late, because, it's Monday night. Okay. Thanks, everyone. And I will see you on Thursday. Bring your questions then. Peace.